The next thing we'll look at is initial value problems and their solutions. The first thing we're going to need is a solution to the differential equation on some interval I. In addition, it's going to satisfy n initial conditions where n is the order of the differential equation. So let's look at some examples. Here's a differential equation, the second derivative plus y equal to 0. And I have my initial conditions, the fact that y of 0 is negative 1 and the derivative of 0 is equal to 1. And I want to show that this function right here, sine x minus cosine x, is a solution to the initial value problem. Since my differential equation has a second derivative, let's start by taking derivatives. We know the derivative of sine x is cosine x, and the derivative of cosine is negative sine. Then when we take our second derivative, we have negative sine x plus cosine x. So let's start by sticking this into our differential equation. We start with the second derivative. We then have plus y, so plus sine x minus cosine x. And that should be equal to 0. And we can see that is satisfied since both my sines and cosines will cancel. We now need to check our other conditions. Let's start with y of 0 equal to 1. So what is phi of 0? We would need sine of 0 minus cosine of 0. We know sine of 0 is 0, and cosine of 0 is 1, and 0 minus 1 is negative 1, which is what we needed. The next thing we need is the derivative at 0. This gives me cosine of 0 plus sine of 0. We know cosine of 0 is 1, and sine of 0 is 0, so when I add these, I get 1, which is what I needed. So this is the solution to my initial value problem. Here's a differential equation, the second derivative minus the first derivative minus 2y equal to 0. And we had previously shown that this c1 e to the minus x, c2 e to the 2x is a solution to this differential equation. So we want to find the values for c1 and c2, where y of 0 equal to 2, and the derivative of 0 is equal to negative 3. So first, let's start by figuring out exactly what the derivative is. We know that my function is c1 e to the negative x plus c2 e to the 2x. Using my chain rule and exponential derivatives, I get that the derivative is negative c1 e to the minus x plus 2c2 e to the 2x. So now let's stick these points in. We know that y of 0 needs to be equal to 2. That gives me that 2 is equal to c1 e to the 0 plus c2 e to the 0, which simplifies to 2 equal to c1 plus c2. For this first derivative, I know that at 0 it should be equal to negative 3. So I get negative 3 is equal to negative c1 e to the 0 plus 2c2 e to the 0, which then gives me that negative 3 is equal to minus c1 plus 2c2. So now we have a system of equations to solve, and we can do that by just adding these two equations together. When we do that, we can see that the c1's cancel, and I get negative 1 equal to 3c2. So I now have that c2 is equal to negative 1/3. And I can substitute that into either one of these equations and get that c1 is equal to 7/3. So now I have my solution. The next thing I want to look at is the existence and uniqueness of solutions for a particular type of differential equation. So I'm going to consider a first-order differential equation, so I need to be able to write it as the derivative is equal to something that's dependent on both x and y. And I want this to be an initial value problem, so I need to know the initial condition, y of x0 is equal to y0. The second thing I need is that both f and the partial derivative of f with respect to y need to be continuous in some rectangle containing x0 and y0. So essentially, I should be able to draw a small rectangle around this point, and both of these functions are continuous in that rectangle. So if these conditions are satisfied, then I'm guaranteed that not only is there a solution, but that solution is unique in some interval x0 minus delta x0 plus delta. So it may not be unique and defined everywhere, but there will be a solution on some interval around this point. So let's see this in action. So here's my first initial value problem, 3 dy dx equal to x squared minus xy cubed, and y of 1 is equal to 6. The first thing I need to do is divide both sides by 3 to actually get this differential equation in the form of my statement of my theorem. Now that I have it's in the right form, I need to know that both f and the partial derivative of f with respect to y are continuous. I can see that f is 1/3 times x squared minus xy cubed, which is just a polynomial, so this will absolutely be continuous. When I take the partial derivative, I actually get negative xy squared, which once again is continuous. So both of these are continuous over the entire plane, so definitely in a rectangle around the point 1, 6. So therefore, we do know that there is a solution for this and that it will be unique. Now let's look at this one. I know the differential equation is dy dx equal to 3y to the 2/3, and y of 2 is equal to 0. I know that f of xy is equal to 3y to the 2/3, which is always continuous, so that's good. The partial derivative of f with respect to y is then 2y to the negative 1/3, which is not always continuous. And the main thing to consider is the point that we need to be concerned about is 2, 0. So y needs to be equal to 0, which is impossible here. It's not even defined at the point 0, so therefore it's not continuous at 0. So this one, the theorem does not tell us that there is a unique solution. It doesn't tell us that the unique solution doesn't exist either. It is still possible that this does have a unique solution, but the theorem doesn't guarantee it.